All right, chemistry, let's take a look at our video lecture for chapter 6, section 4. We're talking about metallic bonding here. Section 3, we really highlighted ionic bonding. And with that in mind, in order to comprehend the things that we need to comprehend today, we're going to have to remind ourselves of what we went over last slide, or should I say last lecture. We ended with this idea that ionic solids are very, very strong. Quite a bit of energy is required to break them apart. But once you apply enough energy to cause a shift in the ion alignment in that crystalline structure, you actually go from having this nice alternating arrangement of positive cations and negative anions. You go from having that nice alternating arrangement, which results in a whole bunch of different electrostatic attractions. You go from that to shifting the lattice over just one ion, but once you move them over one ion, now you have positive to positives next to each other and negatives next to one another. And it results in a huge amount of repulsion within the crystal. And so once you provide this bare minimum, this threshold of force that is enough to shift the ions over one place, you will then experience a large amount of electrostatic repulsion, and at that point the crystal will simply break apart very, very easily. This is what we refer to as being brittle. But moving forward into section 4, talking about metals, metallic bonding, we're going to need to describe the electron C. We're going to need to describe or explain metallic properties. Those metallic properties are malleability, ductility, luster, and conductivity. We will talk about, we're not going to talk about luster very much in this lecture. There is a sufficient description in your textbook, however, and that will be useful later. And then lastly, explain why hammering flattens metals but shatters crystals. That's our last objective for this lecture. That's why we went back to the most recent slides to remind you of why ionic solids shatter when a force is applied to them. And from that, based on that, we're going to contrast that model with the electron C model and why it allows metals to flatten when or bend when force is applied to them as opposed to shatter. So we're going to start with metallic bonding and its lattice structure. It actually does form a lattice. It's a very regular lattice structure. It's a little bit different from the lattice structure that's found in ionic bonds, because in an ionic compound you have alternating ions. You have alternating charged ions. You have cation, then anion, then cation, then anion. In this lattice, you have only positive cations. Only positive cations. You might wonder, well, why don't they repel one another very violently? Because in between the positively charged cations, there is this thing called the sea of electrons, right? So these are metals. These are cations. These are cations because they donated their valence electrons. They got rid of their valence electrons. They got rid of their valence electrons because that was the easiest way to achieve an octet of valence electrons and a noble gas electron configuration. And so they've donated all of these electrons, but because we're assuming that we're talking about a pure metal, right, a sample of only metals, there are no non-metal atoms here. There's no carbon, there's no helium, there's no phosphorus, none of that. Just metals, okay, any metal. Because we're assuming we're talking about a pure metal sample here, there are no atoms that want to take up those electrons. There's no fluorine that wants one more electron. There's no oxygen that wants two more electrons. And so there are no atoms that are going to take these electrons in. So what they do is they're kind of relegated to moving in between, kind of like this interstitial area here, in between the positively charged cations. Now, because they can move freely, we refer to them as delocalized. Delocalized. They don't have one locale. They're not attached to any particular positive cation. So this is metallic bonding. When the metal atoms become positively charged cations, they are then attracted to that negatively charged sea of electrons. it is this attraction that we call metallic bonding. Now, we need to talk about metals' high melting points and boiling points. This is due to the very, very strong attraction between the negatively charged sea of electrons and the positively charged cations. There's a very, very large electrostatic attraction there. And this property results in high melting points. Okay? The high melting points, the temperature at which the solid turns to liquid, and boiling points, the temperature at which the liquid turns to gas, are very, very high in most metals. There are some metals like mercury, for example, that is a liquid at room temperature, but that's not the norm. Most metals have very, very high boiling points and melting points. Again, this property is due to the strong electrostatic attraction between positively charged metal cations and the sea of electrons. It's so strong, in fact, in order to overcome those attractions and move from the solid state into the liquid state, you're going to have to provide a temperature of over 1,000 degrees Celsius. In order to move from the liquid state into the gaseous state, you're going to have to provide a temperature of almost 3,000 degrees Celsius. Incredibly high temperatures, because there's a lot of energy required to overcome that electrostatic attraction and move into the next phase. Now let's talk about conductivity. Remember, we have delocalized electrons here. So we have delocalized electrons within these metallically bonded cations. It's this delocalized nature of the electrons that allows metals to conduct heat and electricity. For example, when a metal is heated, when we add heat to it, the delocalized electrons gain kinetic energy. That's what heat is. It's kinetic energy, energy of movement. So they're moving faster, right? These electrons that have gained this kinetic energy, they've gained the heat, they're now moving faster. And so they move through the metal sample faster. And they're therefore transferring the heat that they have with them, the kinetic energy that they have with them throughout the metal sample, and they're doing it very quickly and very easily because, remember, they're moving through the sample freely. They are delocalized. Metals conduct electricity much in the same way. Because remember, electrical current is simply the ability of charged species to move. Now, ionic compounds can conduct electricity as long as they're either dissolved in water or in the liquid phase, because in the liquid phase, those charged species, the ions, can move. They don't conduct electricities in the solid state, because remember, in a solid state, the ions can't move, right? So ionic compounds, right, made of ions, they conduct electricity when they're in the liquid phase because the charged species can move. When we move to look at metallic bonding, there is a charged species that moves very, very freely. It's the electron itself. Remember, they're delocalized. They're free to move. And so as long as they can move, they can flow in one direction. And if they flow in one direction, that is an electrical current. And we'll end with this idea, introducing the idea of malleability and ductility. Malleability is the ability to be hammered into sheets, generally referred to as the ease with which you can shape something. And ductility, which is the ability to be drawn into wires. Both metals and ionic compounds are strong. And when they're in the solid phase, they're both very, very strong. Ionic compounds, however, are brittle. Metals are not brittle. When a metal is hit, the layers of the metal ions are able to slide over each other, so the structure does not shatter. But why would the metal cations be able to slide over one another? Notice, as these metal cations, they were in this arrangement, their normal lattice structure right here, as they shift to the right, because the electrons in this kind of interstitial area are able to move freely with the cations as they shift, that means that the electrostatic attraction is never lost at any point. Remember back when we showed the ionic compound, the ionic solid shattering because like charges lined up with like charges? Here, the negatively charged electrons stay. They're able to move with the cations as the cations move. And so that source of the electrostatic attraction never goes away. So you can reshape these things, and we never lose electrostatic attraction. That is why metals are not only strong, but also malleable and ductile. All right, let's go for some checks for understanding here. These are true or false. Number 1, metals have a lattice structure. This is true. Metallic bonding is an attraction between metal ions. False. If it was only metal ions, you'd have electrostatic repulsion. Metallic bonding is an attraction between metal cations and delocalized electrons. Number 3, electrons have fixed places in the sea of electrons. Now, if you said true to that, I should probably kick you out of class, because the main thing we've been focusing on here is that the sea of electrons is made up of delocalized electrons. All right, so number 3 is false. Number 4, metallic bonding allows metals to conduct electricity. True. Number 5, metallic bonding allows metals to be bent. True. Metallic bonding lowers the melting point of metals. That is false. All right, chemistry, I will see you next period.